I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on Introduction to Plane Electromagnetic Waves for the course Electromagnetic Fields and Waves. So now we see the uniform plane waves. An electromagnetic wave originates from a point in free space, spreads out uniformly in all directions, and it forms a spherical wavefront. An observer at a large distance from the source is able to observe only a small part of the wave, and the wave appears to him as a plane wave. So, for such wave, the electric field E and the magnetic field H are perpendicular to each other and also to the direction of wave propagation. So, a uniform plane wave is defined as it is the wave in which the electric field and magnetic field has lie in a plane and have the same value everywhere in that plane at any fixed instant. And for uniform plane wave, considering it is traveling in z direction, the space variations of E and H is 0 over z equal to constant plane. And this implies that the fields have neither x nor y dependent. That is, we can write dou by dou x and dou by dou y is equal to 0. A plane wave is transverse in nature, that is, the electric field and magnetic field are both perpendicular to the direction of wave propagation. So that these uniform plane waves are called as transverse electromagnetic waves. And this is the picture of the uniform plane wave where the electric field lies in vertical direction and the magnetic field lies perpendicular to the electric field, that is in horizontal direction. So, for a uniform plane wave, always the electric and magnetic field vectors are perpendicular to each other, and also they both are perpendicular to the direction of wave propagation, so that a uniform plane wave is otherwise called as transverse electromagnetic waves. So now we are considering a uniform plane wave is traveling in the direction of x-axis. So the electric field has the component Ey in the direction of y and magnetic field H in the direction of Hz in z direction. And it said that the wave is polarized in y direction because we know that the polarization always depends on the direction of electric field. In this case, we are assuming the plane wave is propagating x-axis, so the electric field is in y direction. So we can say that the wave is polarized in y direction. And for this case, considering the medium is a non-conducting medium or free space, the conduction current density J is equal to 0 because J is equal to sigma E, where sigma refers to conductivity. For non-conducting medium, conductivity is 0. So, the Maxwell's equation, which is derived from Ampere's law, has only the displacement current density dou d by dou t. And so, del cross H can be written as dou d by dou t is the equation 1. And we are expanding this in rectangular coordinates, and we get minus y into dou hy by dou x equal to y vector dou dy by dou t. And similarly, we are having Maxwell's equation derived from Faraday's law is del cross E is equal to minus dou b by dou t. And this also have expanded from matrix determinant, and we can get dou Ey by dou x equal to minus mu dou hy by dou t. So now the previous equations of Hz is the time derivative of Ey, and equation 8 is the space derivative of Ey to the time derivation of Hz. So we are obtaining from equation 8 dou squared Ey by dou x squared is equal to minus mu dou by dou x of dou Hz by dou y. And similarly, from 4 we get dou by dou t of dou Hz by dou x equal to minus epsilon dou squared Ey by dou y square. And now dividing by mu both the sides, we get minus 1 by mu dou squared dy by dou x squared is equal to dou by dou x of dou hy by dou z. So equation 9 does not matter whether we differentiate first with respect to x and then with respect to y, or it can be vice versa. So finally we can write dou squared dy by dou t squared is equal to minus 1 by mu epsilon dou squared dy by dou x squared. And this is equation number 12, relates space and time variations of scalar magnitudes of Ez of the electric field intensity, and is called as the wave equations of Ey. And another equation we get in terms of magnetic field, we get dou squared Hz by dou t squared is equal to 1 by mu epsilon dou squared Hy by dou x squared. And this equation 13 and 12, both the equations, second order partial differential equations, are called as wave equations for plane electromagnetic wave, and they are also called as D'Alembert's equation. And now the parameter 1 by mu is nothing but the velocity of the wave, the whole square, that is v squared is 1 by mu epsilon. We know v is the velocity of the wave, mu is permeability, and epsilon is permittivity. So by substituting this, D'Alembert's equation becomes dou squared Ez by dou t squared is equal to v squared dou squared Ey by dou x squared. And dimensionality, we get volts per meter second squared is equal to v squared volt per meter squared. So solving this, we get the velocity meters per second. And the uniform plane waves is a very idealized case. It can adequately model many practical situations in wireless communications, radars, etc. So that uniform plane waves are used for the analysis of many practical situations of communication engineering. And for example, when the fields impinging on receiving antennas that are far away from transmitting antennas are practically uniform plane waves. Now assessment questions. The properties of uniform plane waves, we know that their electric and magnetic fields are perpendicular to each other and also perpendicular to the direction of wave propagation. Is one of the main important property of uniform plane waves. And D'Alembert's wave equation we have derived, and the uniform plane waves are useful in the analysis of communication engineering. Thank you.